All right, we're going to start Chapter 3, and Chapter 3 is all about numeric distributions. Remember, we categorize our data, or we classify our data, I should say, as either categorical or numerical distributions. And so 3.1 is looking at specifically symmetric distributions and how we're going to summarize them. I'm going to come back to these bullet points in a second, but I want to just refresh your memory that when you're working with numerical data, we always describe the distribution using three main characteristics. So the shape would refer to either whether the distribution is symmetric or skewed. And along with shape, we may discuss the mode, if it's unimodal, bimodal, multimodal, etc. The center we can think of as a typical value, something that represents the distribution. And then the spread we can think of as the horizontal variation or variability. Remember, I use those words interchangeably. Let's see, variation, we'll go with that. And literally, how far apart is the data? Are the data points really spread out, or are they clustered somewhere near the center? So the two measurements we're going to focus on in this section are the mean and the standard deviation. So when we're working with a symmetric distribution, the mean is what we're going to use as the measure for the center. And then the standard deviation is what we're going to use as the measure for the spread. So in Chapter 2, when we look at, say, a histogram, we might just kind of eyeball it and say, well, the center looks like it's somewhere between, this number and this number. And we'd compare the spread. This distribution looks like it's farther apart and more spread out than this distribution. Now we're going to have a little bit more concrete way of looking at those two measurements. So when it's a symmetric distribution, remember, we're going to use the mean and the standard deviation. Okay? So you've probably heard of the mean. I would imagine you've done that somewhere in your math career. Let's take a look at this example, and then we'll get into the mean. So we're looking at the dot plot of a fictitious distribution of test scores for a sample of students. So first of all, it asks us, how would you describe the shape of the distribution? So in general, shape, we're either going to focus on whether it's symmetric or skewed. And hopefully you look at this and would say, okay, we've got this peak in the middle, and then it kind of tapers out on both ends. It doesn't have to be perfect. It's very rare that you're going to get a perfectly symmetrical distribution, but something that's close to it like this, we could say is roughly symmetrical. So roughly symmetric. What is a good measure of a typical value? And there's one descriptor that's missing from this picture, and that's this dotted line. So this dotted line actually represents the mean. And if I remember from this example, I believe this dotted line represented a value of around 24.5. So with that in mind, knowing that that right there corresponds to the mean for this distribution, would you agree that the mean would work as a typical value? And I would say yes. So we're going to say a good measure for the typical value would be the mean, and if you want to add it to your notes, I'll tell you, you wouldn't know this just by looking at it. This would have to be provided. But the mean in this picture was about 24.5. And because it's symmetric, we're going to go ahead and go with the mean as a representative of the typical value. I think even if you didn't have the mean there, you probably would have said somewhere between 24 and 25 would probably have worked for your typical value. Okay, let's take a look at the next example. So an accounting firm is looking over the exam scores of the certified public accountants of its tests of its applicants. The results are recorded in the histogram below. So one thing that's missing again from this picture is the mean. So I'm going to go ahead and tell you what the mean is. You wouldn't be able to calculate that just by looking at it. If you were doing the mean, you'd have to have all of the data to work with. By hand, I don't think I would ever ask you to actually calculate the mean. We'll use StackCrunch to do it, or we'll give you that information. But the mean here, I'll tell you for this data, is 49. So let's take a look at the questions. It says, what is the shape of the distribution? And I hope that you would see, again, we're dealing with a symmetric distribution, or roughly symmetric distribution. And so for that reason, the mean is going to be a good measurement of the typical value for these applicants. So part B says, what is the typical score? Remember, typical means center. So what is the center of the applicants? And so would we agree, if 49 falls right about there, that that would be a reasonable representation for a typical score? And yes. So the moral of the story is if you're working with a symmetric distribution, you're going to use the mean as your measurement for the center. Let's take a look at another example. So the histogram below shows the distribution of salaries of NBA players for the 2017-2018 season. Now here they're giving you some data. They're telling you that the mean salary is a little over $5 million. The median salary is a little over $2 million. Now we haven't really talked about what the median is, but just go with those numbers for a second. Let's look at part A. It says, how would you describe the distribution? So I hope by now you see this is definitely not symmetric. What kind of a distribution shape would this be? And we would say this is skewed right. And salary data is going to often be skewed right because most people are going to be below a certain amount, like right in here. And then you've got some people on the higher end that are making, a lot of money, but most people are below a certain amount. So salaries are almost going to be right skewed. Do you think the mean would be a good representation of the typical salary for these players? So let's do this. Let's go ahead and mark where the mean would show up, knowing that it's around 5 million. So 5 million is here, so about 5.7 million looks to me like it would be somewhere, I'm guesstimating, somewhere right about there would be the mean. Let me label that. So that's our mean. And then the median would be only around 2 million, so the median would be somewhere down here. I'm going to just call it the median. Which one do you think would be a better representation this time for the typical value for these NBA players? Well, hopefully you say that the median in this case would be a better representation. The mean, unfortunately, is going to be artificially, I shouldn't say artificially, but it's inflated by these players who are making more money. So do you think the mean is a good representation? No, since the higher salaries are raising the mean. Even though most of your players are down here, that's where I would say your typical value is somewhere in that category. So the median would probably be a better measure. So since higher salaries are raising the mean. All right. So again, if it's symmetric, we're going to go ahead and use the mean, but if it's skewed, we're going to use the median, which we'll talk about in the next lesson. So summary, using the mean to describe typical values. So when the distribution of the data is symmetric, I'm going to abbreviate symmetric, the mean represents the typical value in the data set. When the distribution is skewed, like we saw in that last example, the median is the more appropriate estimate of the typical value. And we'll talk more about the median in the next lesson. So computing the mean. So the mean you've probably heard of as somebody referred to as the average. If you're looking for the average of, say, your test scores, you're going to add up the test scores and divide by the number of tests that you took. It's the same idea here. So for a small data set, first of all, notice the symbol. So the symbol, we would call it X bar. So X bar we could think of as the sum of each individual data point, whatever it is, up to the nth data point, divided by however many data points we have. Most of the time we're going to use StatCrunch. So when you're doing the homework, you're going to use StatCrunch to do that. And then, of course, if it's a test or something, we'll probably give you the mean and ask you to do something with it. So let's look at a quick example here. It says, below is the dot plot of a sample of prices for a gallon of regular unleaded gas at 48 gas stations in St. Augustine, Florida. So we've got a dot plot here. This definitely does not look to me like it's symmetric data, but just for practice, they're saying calculate the mean using the formula. And I'm going to do this quickly here because I'm going to skip the details. I just want you to see what the mean is. But here's what we end up with. We would have X bar is equal to, these first two dots are $2.61 plus another $2.61. Dot, 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 I'm not going to write all these out, up to the highest value, which is $2.89, and there were 48 gas stations, so we have 48 points in our data, so we're going to divide all of that by 48. Again, you're not going to have to do this by hand, I just want to give you a quick example. This gives me an approximate value of $2.75. So the mean price of gas for this sample is 75 cents. Interpret the price of gas, or interpret the mean of this in the context of the problem. We could say a typical value, or I should say, maybe not value, let's say a typical price is $2.75 for a gallon of gas. Now, I will say I'm not sure that this is exactly a symmetric distribution. It looks to me like I would say it's skewed right. So I'm not sure that the mean, I'm sorry, not skewed right, skewed left. I'm thinking like this. I'm not sure that the mean is necessarily the best measurement, but I just wanted to show you an example of computing the mean by hand. I'm going to skip part C for right now because I want to talk more about that later on. So how do we calculate the mean using StatCrunch? So pay attention to these directions because this is what you're going to follow. Once you have your data in a particular column, you're going to go to Stat, Summary Stats, and then Columns, select the column, and then you're going to click on Mean and Compute. And you'll see this when you're working on the homework or when we're in class. We'll practice this together. So continuing from the example 3.14, what is the mean of the data set computed using StatCrunch? Again, you don't have StatCrunch in front of you, but I believe the answer was about the same. I think it was about $2.75, and it should be the same whichever way we're doing it. Let's talk about the spread. So if it's a symmetric distribution, what are we going to use to calculate the spread? This time we're going to use what's called the standard deviation. So remember, if it's a symmetric distribution, we're going to use the standard deviation to talk about the spread. The spread, remember, refers to the variability in the distribution. Horizontally, how far apart are the data points? Are the data points really separated, or are they all clustered around a particular value? Okay? Oftentimes we need to know, so let's write this down. We need to know if the data, sorry to leave myself much room here, if the data is near the center or not, or far away from it. So let's look at this example. The following histograms recorded the daily high temperature in degrees Fahrenheit in 2017 for St. Augustine, Florida and Mount Pleasant, Michigan. So how would you describe the shape of each distribution? So for St. Augustine, I would say this is probably skewed left. If you'll notice that it starts off, it kind of has a tail, increases, and then just kind of drops off. So I would say there's a tail here. So I would say St. Augustine is skewed left, or left skewed. Mount Pleasant, there's some weird stuff happening here, but I would say we could probably describe this as roughly symmetric. Very roughly symmetric. Which distribution appears to have more spread horizontally? So I don't know what the standard deviation is for either one right now. It's hard to compute that by hand, and I can't tell that just by looking at the histogram. But just think about looking at the range of temperatures. St. Augustine ranges, it looks to me, from about a low of about 41 through a high close to 90, I would say maybe 89. Whereas for Mount Pleasant, the temperatures drop a lot further. The temperatures go down to, it looks like about 10 degrees until, I don't know, maybe about 88 degrees. So just looking at the ranges that way, which one would you say has a larger spread? And I would say it's Mount Pleasant. So Mount Pleasant has a larger spread horizontally. So one way we can measure the spread when we're dealing with a symmetric distribution is to use the standard deviation. So I'm going to give you a formula for the standard deviation. And the good news is I'm not going to ask you to compute this by hand. I'm just giving it to you so you have it in your notes. It's the sum, sigma, that's a Greek letter sigma, means sum, of each individual data value minus x bar quantity squared. Do you remember what x bar was? X bar, remember, is the mean. Divided by n minus 1, where n refers to the sample size, however many points you have in your sample. For most distributions, a majority of the data will fall within one, I'm going to abbreviate, standard deviation of the mean, and we'll talk more about what we mean by that in a little while. The standard deviation can be thought of as a typical distance. The observations are away from whatever the mean is. So it kind of gives us a distance. It is a distance, really, that the values sort of on average, I use that word loosely, are away from whatever the mean is. So a typical distance for the observations from the mean. So let's take a look at this example. Below is the distribution of the amount of particulate matter or smog, that should say smog, S-M-O-G, so pollution, in the air in 328 cities in the U.S. in 2017 as reported by the EPA. The mean particulate matter is 8.3 micrograms per cubic meter. We don't have to worry about what that means. Maybe science majors, you might need to know that eventually. But right now, let's write that down, that X bar, the mean for this sample, is 8.3. The standard deviation for the sample is 2.36. And by the way, I used the symbol for standard deviation, but I didn't really highlight it. For a sample, the standard deviation symbol is a lowercase s. So the standard deviation s is 2.36. Would you agree that this is roughly symmetric? It's not perfect, but it comes up to a peak and then it tapers off. So it says find the smog level 1 standard deviation above the mean and 1 standard deviation below the mean. So what I'm doing is I'm taking the mean value and I'm going to add and I'm going to subtract the 1 standard deviation. So let's do the lower bound first. 8.3 subtract 2.36 gives us a value of 5.94, and then 8.3 plus 2.36, so remember the mean is somewhere in the middle, actually that's where this line is, that's 8.3, and then the upper limit would be 8.3 plus 2.36, which is 10.66. According to the EPA, smog levels over 12 micrograms per cubic meter are considered unsafe. What can we conclude about the air quality of the smog most of the cities in this sample? So a few minutes ago we said that a majority of the data in its distribution will fall within 1 standard deviation of the mean. So what we're saying here is the majority of this data will fall somewhere between these two numbers, 5.94, so maybe like right over here somewhere, and 10.66, maybe right in here somewhere. So the majority of our data in our sample is going to fall between those two numbers. So what does that say about most of the cities in our sample? If 12 is the level of unsafe, are we good for this sample? Are most of the cities safe? So I would say yes. So what can we conclude? We can say that most cities in this sample are safe because they fall between 5.94 and 10.66, and 12 is the cutoff for unsafe levels. So we are good to go here. So how do we calculate the standard deviation using StatCrunch? This is the way you're going to do it. I'm not going to ask you to calculate it by hand. We're going to go to that summary statistics menu again, select the column, select standard deviation, and then compute. So we're going to use StatCrunch to do this every time we need to compute a standard deviation. So it says use StatCrunch to compute the mean and standard deviation of the data from the example we had earlier, so the one with the gas stations. These are the gas stations. And I'm going to skip going to StatCrunch for now, but I'll tell you if we did go to StatCrunch, it would be giving us a value of 0.064, it looks like. And because, remember, we were looking at prices, I'm going to round this to 0.06, that's cents, 6 cents. So if you'll recall, the mean for the gas prices was $2.75 per gallon. So what does this mean? This means that most of the gas stations in the sample are going to fall within 1 standard deviation of the mean. So we can say are going to fall within, I'm going to go ahead and do 6 cents because that's the standard deviation of the mean of $2.75. So most of the gas stations are going to be somewhere between 6 cents less than that, so $2.69 to $2.81. That's where most of them are going to fall. Make sure you see where I'm getting that. I'm doing 75 cents, take away 1 standard deviation is $2.69, $2.75, add 6 cents, 1 standard deviation gets me to $2.81. The last little section here, the variance, and all you need to know right now is that the variance is the square of the standard deviation. We're not going to do a whole lot with variance in this course, but I just want you to have that formula somewhere in your notes.